Special thanks to Jake, who decided to join on this. He comes from a Y Combinator company called Luminal. He'll be speaking second. And then we've got Chris. Yeah, Chris, why do you call yourself the Wiz? Yeah, where did that come from?
I don't call myself that, to be clear. Uh,
Hilarious.
my co-founder and CTO at Makerspace calls me that, and it's part of the brand, so we leave it up. Yeah.
Yeah, gotcha. Because that's in your LinkedIn, which is hilarious. Okay,
Sure.
so this is the quick intro part, talk zero. Not going to spend too much time. Antje unfortunately had a pretty critical meeting that coincided with this exact time slot. Just so you know, the like AWS reInvent, which is where Antje works and where I used to work, is coming up. There's a whole lot of Gen AI and cool stuff coming out, brand new agentic models. I hear are on the horizon. So check that out. And then the first talk is going to be by Chris. He's going to talk about Dynamo, which if you come from an AWS world, this is a different Dynamo. And so Chris will explain what this is. The second session is going to be high performance PyTorch, CUDA optimizations, and CUDA search, and that's going to come from Jake at Luminal. So I think each talk should be about between 20 and 30 minutes. We'll take Q&A in between the talks. I'll try to answer as much online, and then I'll summarize after each of your talks as well and get you folks back on to answer. We'll try to go to the top of the hour. Chris, take it away, bud.
Yeah, what's up, everybody? My name is Chris Alexiuk. I'm a product research engineer at NVIDIA, which is a very fun made-up title. But the the basic idea is straightforward. I work at the intersection of those three things, so product research and engineer. Very fun stuff. And what I'm going to talk about today is something called Dynamo. And I'm going to go ahead and share my screen, and I'll send that request to Chris. And the idea here is like Dynamo is a platform for scaling generative AI real fast, right? So the big idea is that you can use Dynamo to make AI go burr. We're gonna use terms like AI because I'm fully marketing pilled by my organization, but I mean LLMs for the most part, if you're wondering. And so the big idea with Dynamo is that obviously we have some hardware that is we like to think is very good at NVIDIA, and then we want to provide inference software that makes it go fast. And we have, of course, we want to open source a lot of this Dynamo stuff, so it's open freely on GitHub. You can submit PRs, whatever you want to do. It doesn't get better without the community. So we're gonna very briefly, because this is the slides, we're gonna very briefly talk about how LLMs work. I understand everybody here definitely knows how LLMs work, but yeah, we got to pay the piper a little bit to context set. And then we're gonna talk about like why Dynamo is something useful. We're gonna talk about a specific mode of Dynamo, which is going to be this idea of disaggregated serving, which is a very fun word that we'll cover. So how LLMs work, you get it. The idea is we put tokens in, we get tokens out. Every step we get tokens. There you go. So I think we're all caught up to speed there. There's this slightly more complex construct called the KV cache, and the KV cache is something that maybe a year and a half ago or whatever was fancy, but I think at this point everyone gets it. The idea is the way that transformer networks do inference, we can actually cache some of the work done for each decode step, and we can keep that hanging around, so we don't have to recompute it. The big idea here is that so instead of doing more work, we do less work, right? KV cache, classic caching. I think probably for the most part people are up to date on KV caching. Then we have the two phases of inference. Okay, so this is also something everyone's very implicitly aware of, and I imagine from a technical sense also quite aware of, which is this idea that we have two parts of our inference motion, right? So we have prefill, which is kind of the stuff that we put in to the context window. We have the idea that, you know, there's a lot of tokens that need to get into the GPU and need to go through the process of being computed, right? And so that's the second step, which is decode. Decode, aka generation, aka sampling, whatever word you're going to call it. But the idea is that, you know, this is where we've already loaded our memory up, right? Our GPU memory up, and now we're just doing math. We're doing a ton of math. We're spitting out tokens, and we're doing it again, doing it again. We're heavily leveraging the KV cache, hopefully, and this is the idea. So this is our two phases. This is the reason. I mean, it's going to blow your mind, but the whole reason we're talking about these two phases is because disaggregated serving is going to come in very handy here. LLM has some metrics that we most often think about when we're talking about performance, as in speed, as in how fast are we crapping tokens out, which is governed by each of these phases in some sense. So that's prefill, which is going to govern kind of the time to first token, and then our tokens per second is going to be governed kind of by that decode phase. So the idea is, right, when we have these two phases, they govern a different set of metrics. And so this is why it's important to care about both. And something we're going to talk about in a minute is that they're not the same. They're not created equally, right? So let's talk about the kind of requests or the kind of pattern that we're going to talk about today, which is request batching. This is the idea that we have the ability to submit multiple requests to our inference backends, and they're batched together. Now, why is this important? The devil's in the details for a lot of inference, right? Like a lot of the time that we're talking about how do we make inference faster, what we're really saying is how do we reduce lazy GPUs that are just kind of sitting around not doing anything, right? So for something like Dynamo, this is a big part of the puzzle, right? How do we get rid of all of these kind of like ugly blocks that that appear that are empty and not doing work, right? So for static batching, there's an obvious kind of limitation here, and then for continuous in-flight batching, we're going to go ahead and we're going to try to ameliorate some of that by closing down these little boxes, right? So obviously this is going to be most dependent on what environment you're doing your inference in, but we're really happy when we see no empty white boxes of lazy GPUs not doing any work. This is okay. So now this is like the most important slide, right? Because it context sets like the entirety of the motivation for disaggregation. So the idea is that prefill and decode have stark differences in the way that they're actually computed, right? This goes all the way down to the bottom, right? So let me just see if this is better for you guys. From Robert's comment there, the idea is that even down to like the kernels that make these things go burr, right? There's differences between prefill and decode, and what this means is that there's some amount of inefficiency, right? If we're doing both of these things on the same hardware. So for instance, right, prefill, we can parallelize the hell out of it. We can just shove all the tokens we want in at the same time. It doesn't really matter. A decode, less parallelizable, obviously across requests vary, but for individual requests, less so. Though, of course, modern architectures get away with some of this, right? We have some made some optimizations in regards to parallel decoding, but the idea is that like we have we have different sets of optimal parameters for prefill versus decode on the hardware. We have different sets of kernels for prefill and decode on with the hardware. So the question then becomes, if we're doing this all at the same time, we're going to have many spaces where the GPU is being lazy, right? Where we're just loading stuff, or we're switching things, or we're all of these things that, make you cringe and wake up in a cold sweat at night, knowing that you're not utilizing your GPUs well. And so this is what disaggregation is meant to help solve, right? Instead of doing this sequential operation on each piece of hardware, we're actually going to disaggregate it, right? I'll do the thing, right? So aggregation is to collect things together. Disaggregation is to split them apart, right? So we're going to disaggregate these operations across different pieces of hardware. The other thing to keep in mind here is that you're going to notice we're talking a lot about this batched world that we live in, right? And this is because this is not something that's going to have really any realistic, use case if you're just running one thread, one request, right? You're not going to get much out of this, right? So we're talking about situations where you have some amount of batching going on. So the idea is pretty straightforward, right? We're going to prefill across a number of pieces of hardware. We're going to keep different caches for those prefill stages or slices, and then we're going to put them into a decoding queue, which is going to be able to take those generated slices, and then it's going to be able to decode from them. Obviously, there's going to be a number of gains here. The other thing that we want to think about is KV cache reuse. So KV cache reuse is really important because we don't want to just kind of restart things, right? We want to think of our KV cache as like an actual cache. I saw Fregly say in the chat there that the book's going to talk about KV caching, so I won't spend too much time here. But the idea is pretty straightforward, that like this should operate like a good intelligent cache, right? We should have some amount of understanding of what's going to be the most used or leveraged piece of information, and we should have an understanding of what won't be, so that we can make sure KV caches all hits, right? We want all hits all the time, of course. Okay, so now we get into some fun charts. Look at all these GPUs. So we have tons of GPUs, and we have tons of stuff that we're doing. And this is kind of test time compute is a big motivation for the Dynamo team to have kicked this into a booter drive. So the idea is, right, with the idea of test time compute, we have this new this new kind of inference pattern, right? Which is we have ultra long context coming in, right? People are dumping everything into kitchen sink into the context window, and they're asking to produce a crap ton of tokens. Things like deep research, things like just a multi-turn conversation with the reasoning model, right? Our contexts are they're exploding very, 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 very fast, right? We're not just keeping in context the messages, though that's one way you can do things. We also potentially want to keep the reasoning traces in context. We want to keep the idea that the model's seen some of this before in context, right? And so all of these things are motivations to move towards making inference go BERT, and specifically disaggregated serving. So this is a marketing slide, so we'll just skip it. It's just saying, here are some things, and disaggregated serving solves all of these things. Okay, that's great. We love to see it. So the main thing, again, we're talking about more load for disaggregated serving is more betterer, right? So as we scale into kind of this this kind of like reasoning paradigm, or we scale into even better for disaggregated serving, extremely huge prefill, right? Where we're talking about like, hey, we just dumped the whole monolith repo into context, and now we're going to do some generation, right? Or we're talking about dumping in, X, Y, Z gigabytes worth of text into the context window, right? This is where this is going to be extremely powerful. Of course, if this is a repeated operation, it's going to be even more powerful, right? So if I'm in an organization and I'm building some kind of inference system that has the idea of this, knowledge source that I want my entire organization and its customers to use, right? And that knowledge source is huge. Obviously, disaggregated serving is going to be a huge benefit. Chris asked a great question. How does Rubin chip change the disaggregated question? Basically, it's built specifically, or it's being built specifically for prefill, right? It is meant to be very good at that. So this is one of the beautiful things about hardware. As we understand our use cases better, we're going to be able to extend hardware to be even better at the things, right? Specialist hardware, even better at the things that we think are important. In this case, Rubin context, right? It's in the CPX title is going to be extremely effective at that. Yeah, great question again from Chris. When is the decode equivalent GPU coming out? If there's an announcement on it, I'll send it to Chris and he'll let you guys know. So, okay, this is the kind of idea of disaggregation. So this is, I am, of course, I've got the logo on the slides. I got Team Green in my heart. So we have to be fully transparent. If you're on if you're not running at large scales, disaggregated serving is not going to be as useful to you, right? So it's not going to be the best. It's not like disaggregated serving is always the right thing to do, right? This is something that's very I think is a burgeoning part of our inference focused world, right? So we kind of come from LLMs do this thing, LLMs do this thing, and that we got very good at making them do one thing. And now we're understanding actually each of these use cases, we should think about them differently. So if you're on one node, especially if you're at kind of, lower amounts of tokens per user, then disaggregation is not going to be something that's very useful to you. However, when you move to the kind of larger scale operations, you're going to find that disaggregation is pretty well good across the board. One thing you're going to notice in these charts, so this is the classic the classic chart math, right, that we have to do. So we have this cached, uncached OSL, cached, uncached OSL. So what this means is that we're starting with 0 tokens in cache, 3,000 tokens not in cache in the ISL. That's the input sequence length. And then we have output sequence length of 150 tokens. So what this is it's saying that this disaggregation is good when we have the prefill mode, right, outweighing the decode mode. So decode's very fast, prefill is a little bit slower, making the switch bogs the whole system down. So if you're in situations where you have long contexts and you're not outputting as let's say commensurate length, then disag is going to be super helpful for you. Something else that we have with our KV caches, right, is this is just a feature of Dynamo. This is not specific to disaggregated serving, but is certainly part of what makes the magic work, which is this idea of KV cache aware routing, right? So instead of having just a bunch of GPUs and we're just kind of blindly around robin sending requests to to the next GPU or whatever it happens to be, or we're only thinking about like GPU utilization, right? What we're going to do instead is we're going to think about how much of the KV cache is already working in the or already in working memory, right? Or already able to be consumed. And so what we're doing is, instead of routing queries based on just naively like, hey, well, this GPU is not doing a ton right now, maybe actually what we want to do is route to, well, hey, the KV cache here is like, oh, it's already done. It's already chilling, right? We're at most of the work has already been done. So even though that worker has higher effective load, we're going to route the requests there. And this, as you can imagine, right, constructing the correct spread or the optimal spread of KV cache is going to be something that is important and useful, which is something Dynamo can help you to do. Of course, most effectively, what we want to do is make sure that we have workers that have very common, KV cache, or high KV cache hit rate information cached. We want to make sure that we have workers that can handle that load. And of course, you can immediately start thinking, right? Well, then we can get very smart about how we're constructing this topology, and indeed you can. And of course, there's a graph that shows that it's faster if you do this. Classic. We wouldn't be talking about it if it was slower, right? Lastly, it's really hard actually to effectively manage memory, right? So I think I'm coming up to my time here, so I want to make sure I'll leave enough time for the other presenter. But we got a few more slides to crush through, so I'll do that quickly. The big idea here is that we want to have some kind of process to schmooth memory around quickly, right? So we don't want to do it. We don't want to wind up in a situation where we're like waiting forever for memory to be loaded. We don't want the situation where we have, oh my God, it's so tedious. We're just burning time and effort, right? Waiting for these bits and bytes to be flown around. And so this is what memory management is a huge part of this puzzle. And so we have Nixel to help us do this. And that is basically just, it's fast to transfer data between nodes. And that's the way we do. So the idea here, right, is as we have loads of prefill going on, as we have loads of hardware dedicated to prefill, moving things around quickly, weights, data otherwise, right? So data in our caches becomes extremely important. There's Dynamo. We got a repo. It's right here. You can check it out. It's dope. I'll drop a link in the chat. This is something that you can get started with. Though disaggregated serving is the use case we talked about today, it does a ton more. It is very straightforward to use simply, and then you can get quite complex with it. There's a few questions in the chat that I'm going to take some time to answer now, and we'll start with Chris's question. How does Dynamo work with VLLM, and what is the relationship between Dynamo and the LLMD project? I would need to defer to people on my team for the second part of that question, but for VLLM, yeah, Dynamo does work with VLLM. It works with a lot of different inference backends. It is handling a lot of this kind of orchestration and moving. It's not necessarily going to be explicitly making tokens go burr, and so it works very well with VLLM. There you go. Okay, then we have another question. Production systems serving large LLMs, KV cache routing clearly improves time first token latency. How do you see this approach scaling across multi-tenant environments? The query diversity is high, cache hit rates may drop. What strategies can balance between maximum? Yeah, so this is like, how do we make sure the KV cache is KV cache where routing is like effective? And I think this comes down to the same kinds of things we see in like expert parallelism, right? For our big boy MOE models, it's all about knowing which parts of the KV cache are most important, have the most hit rate. We want to think about things like pooling those towards resources so that we can ensure that we have the most space for kind of out of band or tail requests. I think this is the main idea, right? It's up to you in some sense. Like you can configure this to your exact specifications. But what I would say is like it's just about pooling work so that if we have a lot of novel work, we're not hitting up against a ton of memory operations that need to be done to shuffle KV cache around. Does NCCL consider KV aware routing technique for benchmarking? That's a great question. I'll get you the answer to that question. I don't know off the top of the dome piece. Offloading KV caches across HBM host memory SSD clearly improves time to first token for long context multi-turn conversations and real-world deployments. How you balance the latency overhead of deeper memory tiers SSD with the need to support longer context. Do you see adaptive policies emerging that dynamically choose the right tier per workload? That's a great question. I have no idea. I'll just be honest with you. This is a great question. I'll find you the answer to that, Matagonda, and I will give it to Chris, and then he will share it with his community. Yeah, great question.
Yeah.
Listen, I can say some stuff, but you know, I think this community is someone who's going to appreciate the correct answer as opposed to a answer.
Yeah, and hinting at some of the adaptive stuff, I actually have an entire chapter dedicated to that. A lot of the dynamic and adaptive and sort of RL based have been in the ether for many years, and have started to really show up around disaggregated prefill-decode, being able to allocate. And because like keep in mind when you run a server like VLLM, it's actually able to perform both prefill and decode. Like that worker can do both. It's just putting it into a mode. I think Dynamo works like that as well too, right? Like a Dynamo worker has the code to do it. It's just you dedicate it to one or the other. So all you have to do is just flip a switch, and then those workers can then start doing more prefill or more decode depending on what's happening. The anti pattern there is that too much context switch, or like switching, I should be careful with my terms, but switching roles like that does create a little bit of overhead and starts to put some jitter into the system. But
I did get an answer on that question. We have the answer is TBD. Right now, we always pull from cache. That's the answer. There you go. There you go.
cool.
Yeah.
Yeah, there's a lot of other techniques too, and like again, I do because I had 1 year to prepare for this book, right? Whereas Chris had just a few weeks here, but there's a whole there's lots of different techniques. There's ways to actually change the precision on the fly for your KV cache, right? Because keep in mind that like you could use like a 8-bit KV cache, and the other thing too is that you could also start to change parallelism schemes sort of dynamically. So that there's a whole lot of dynamic type of like behavior. The problem is your KV cache is stored in sort of one parallelism scheme, and if you start to change it on the fly, then you have to make sure that the target and the source can change on the fly as well, and yeah, can adapt to the different precision, can adapt to the different parallelism schemes. So yeah, a lot of cool stuff. I think mostly research stuff right now, but yeah, Chris,
And
man, thanks so
that's kind
much.
of that's kind of one of the things that's interesting, right? Because it is. I think it's a lot more like we're trying to, like with Dynamo specifically, and I know a lot of other people. The actual goal, right, is to come up with a framework that lets you like set or configure a lot of these environment specific needs yourself, and so it's kind of like the race to build like a composable framework to do this, as opposed to building like 6 different presets. And I think Dynamo is trying to step into that role of course it is, right? Trying to step into that role where you're able to describe your environment, and then Dynamo should be able to give you something that is performant, right? You can't say most performant, of course, but reasonably performant, or certainly outperforms other available configurations. And that's I think as we learned that all the way down to the inference stack, all the way down to the hardware, we need to have environment specific configurations. I think this is we enter a impossibly large space of options.
Is Dynamo considered the successor to Triton inference server? Is that official, or I mean, Triton's still supported, right?
Yeah, of course. Yeah, Triton.
Yeah.
Yeah, and I mean, it's designed to work with whatever you're using, right? So if you are, I would, the word replace is obviously very strong, but I think the idea is that Dynamo should be suitable for a lot of your inference needs, but there's a lot of environments that still rock and will continue to rock Triton, and it's our boy. We're not going to stop supporting it. We're not going to stop making it fast, right? That's not in the cards. So
Right. And I know Dynamo is trying to, or it appears that Dynamo is trying to not be the infinitely configurable type, because TensorRT has so many knobs and so many configuration settings that it's often kind of a turn off to folks, and they don't know what they're doing, and they change one flag and it completely affects. So hopefully, yeah, Dynamo finds a good balance between configuration, complexity, and performance, that kind of thing. Right.
yes, and I think people will continue to be pleased with efforts made in both directions as they continue to roll out.
Right on, bud. Where are you based, by the way? Not to dox you, but...
Toronto, Canada.
Oh, that's right. That's right. I
Yes.
hear the process.
That's right. my accent is what I've been told. Yeah. Well, thanks,
Are you
guys.
coming?
It was a blast, and I can't wait for the next presentation.
Yeah, are you coming to the Bay Area? Yeah, anytime soon? You coming to Santa Clara?
Yeah, I'll be there in November, and of course GTC DC
GTC.
is end of October. Come on out if you guys are going to that. Hit me up. I'll be trolling around the conference. So
yeah, are you presenting there?
yes, yeah,
Excellent.
yes, sir.
Cool, bud.
All right.
Have a good rest of the week. Thanks
Thank
again.
You as well.
Jake, you ready? Hop
Yes,
on board.
sir.
Make sure you introduce yourself. Talk about the company. Talk about the product. Talk about Y Combinator. Everyone loves Y Combinator stories. So go ahead. Up to you.
Yeah. Thank you, Chris. So Chris hit me up last week. We actually just had our demo day last week. So it's been a bit of a whirlwind. A lot going on, busy weekend, but I'm really excited to talk to you all about Luminal today. So I just dropped Luminal's GitHub in the chat. Luminal is an open source compiler. And with that being said, let's just jump into the purpose behind Luminal and the stated goal. Right. All right, can everyone see my screen? Great. Okay. Yeah, so Luminal's stated purpose is to never have you write CUDA ever again. So go from very high level PyTorch code or other frameworks down to GPU code, or even eventually PTX. I know someone in the chat's going to ask that. Not now, but possibly in the future. So if anyone here, I'm sure many of you have architected your own models, then you're very familiar with a lot of these error logs that you see on the left here. So the present day experience for developers is you have an AI researcher that writes your model architecture in PyTorch and then hands that off to an ML ops or ML platform team to optimize it. This is really messy. Code doesn't behave the same way in these environments, in these Python notebooks that it does in production. So our goal is to basically obfuscate the need for that handoff and really tighten that pipeline from research to engineering and get researchers writing performant code all in one line of optimization, which is a very ambitious goal. But you think about the landscape today and really what it is, there's kind of three layers to it, I guess. You've got these top level frameworks like PyTorch and maybe less so Keras now and these other ones. And that's just going to get you access to the hardware, right? Just any access at all. And then you've got these DSLs, right? You've got Triton, most famously, I think, right now, as well as I think they just developed one for Cutlass, right? Qt. So you think about it, you kind of go down the architecture, a level of exposure that you get to the architecture, and obviously the learning curve gets steeper and steeper as you go down these DSLs. Luminal's stated goal is really to obfuscate the need for these DSLs and just get you the performance that you get from them from your PyTorch code. Now, ahead of time, we are right now strictly in Rust. We haven't built the Python bindings yet, but that's high up on the roadmap coming up. So just some to set the stage for what we are and what we aren't. Luminal, we're an ahead of time compiler. So there's not going to be, we're not like a torch compile or anything like that. Due to the nature of how we're searching through these kernels, it just takes a long time. So we opt for ahead of time compilation. We're also not using any AI when we're actually discovering these kernels, right? So as opposed to, I think there's been some people that have given talks on using LLMs to search through it. there's a world where that could be possible. Right now, we don't think it's the best approach, although we try not to be dogmatic about any approach. Our goal is really just to spit out optimal kernels. So if that does become the predominant approach, we've got some strategies. We're actually probably in one of the strongest positions if that does become a predominant approach. I can get into why that is when I get into how we construct the search space. But there's just a lot of limitations. Like obviously an LLM right now can spit out flash attention from a naive attention kernel, and that's just because it's seen it a million times, right? But you run into the synthesis problem with this stuff where if you hand it a model whose architecture it's never seen before, right, it's going to have a lot of trouble coming out with performant code, at least very quickly, right? So we think we can do it faster deterministically with search. And then we're also meant to be a drop-in speed up to the inference after you're done with all of your training. A lot of people ask, oh, are you competing with PyTorch? No, we love PyTorch. We think it's a great framework for training. We just think Torch compile is fundamentally flawed. Talk to some people on the Torch team. They're obviously working on their second version of the compiler, and it's going to share some elements with Luminal, it sounds like. So they're kind of coming around to maybe removing some of the just-in-time aspects, at very least extending on what they do there. And then we're open source, like I said before, repos in the chat as well. So here are kind of the vertebrae of the talk today. I'm just going to go over the technical approach at a fairly high level. We can get as deep as we want in the questions, but I'm trying to, for the sake of time and my own sanity, keep it pretty limited today. So getting into, what are the ops that construct the Luminal IR, why we use those ones as opposed to others, to the actual building of the search space using our data structure called an egraph, and then 3, how we profile those kernels and actually find the optimal ones, with 4, how do we actually select the candidate kernels. So getting into the ops that we actually use under the hood, it's a RISC style architecture, and PyTorch graphs have around 1,200 possible operations. So we have 2 orders of magnitude less here. And it turns out you can really build almost, probably 95% of all models out there with just these 12 operations. So, if you want to think about, for example, like the difference between a matmul and a convolution, right? Well, what is that? You've got some adds and multiplies and a sum reduce, right? Broadcasted across an array with an aggregator that you're keeping track of. And that's really all you need. They're fundamentally kind of the same operation. So you don't need 2 separate operations to do that. And that's provides us with a lot of flexibility for how we can rewrite the IR to find some interesting optimizations, which is why we opt for the flexibility and then constrain it later. And getting into the egraph, this is a kind of up and coming data structure, which is a funny thing to say. You don't really hear that often. But it's very powerful in that it can perform a technique called equality saturation. So what that means is, given some defined rules, they call them rewrite rules in the language, you can basically construct the set of equivalent graphs that can equally represent the mathematically equivalent but distinct representations of the graph. So this is a very simple approach. It's on their website. I'd recommend going here, by the way, to actually play around with them. It's a great demo that they have on there where you can actually write some egg and egg log and play around with how the graph gets rewritten and reconstructed. There's a nice visualizer to show you. But this example here is actually showing how a times 2 divided by 2 can be rewritten multiple ways. So I believe they're using the identity principles here of multiplication and division to rewrite these, and all of these clusters, these dotted lines, are just the different pathways that it's seeing to rewrite them with, and moving around the edges accordingly of the nodes. So actually, I'm going to back out here, and I'm going to actually show you this in real time just to show you how cool this is. So here we go. This is the demo from our repo. You can actually access by going to the demos and then matmul folder. And I'll run it here. And this is compiling to Metal. And so what we're seeing here is in real time, using the rewrite rules we've constructed, it's spitting out all of these equivalent kernels for, I believe it's I believe this is like an MLP with a swish activation layer. Yeah, it is actually. So you can see that it's kind of playing around with the memory, it's playing around with the looping structure, all these sorts of things. And this is real time, by the way. It's profiling each of these on my MacBook using Metal. So Metal is of course Apple's kernel language. Let it finish up. Perfect. And then it spits out, this is our graph visualizer. So this is something we just started working on. We plan to make it a lot similar to some other visualization tools you might have seen. But basically the whole idea is you can actually see, what the optimal graph looks like. Eventually we're going to have kind of like the precompiled graph and the compiled graph. But really interesting here is, it found that it can use the tensor core that's within my Mac, right? So to do this TC matmul, that's obviously going to be a fantastic speed up, and also here in the activation layer as well. Yeah, and the whole idea is, you can kind of see iteratively as we go through this, and this is fun. You can just drag it around, have a lot of fun with this. You can just see iteratively what the compiler is doing to actually find these optimal graphs. This is the same thing. So what's the catch? Obviously, the search space explodes. It's probably, I'm sure I haven't even looked at the chat. I'm sure that's already been asked. And there's a few ways you constrain it. So the first is when you're actually constructing the equality saturation. When you're writing those rules, you want to make sure that those rules are intelligent to the hardware that you're trying to tap into. So we have different rules depending on the hardware target. Obviously, you just saw Metal there, but we've got different ones for CUDA. And eventually, the goal is to cross compile to other more exotic hardwares as well. And then once you have that constructed search space, how do you step through that, right, in a way that isn't going to take days or hours? So the first approach, right now, to be honest, this is where the most work needs to be done. And like I said, we're open source, so if you want to help us with that, feel free. But there's a lot of precedents for how to do this, right? So most famously, we took a lot of inspiration from AlphaGo with this project. You can use Monte Carlo tree search to create, kind of those clusters of areas to search rather than having to look over the whole thing. Obviously, we can also learn reinforcement learning to find the best paths, and then in the future, just static profiling as well. So the end goal with this, I forgot to mention, is kind of become like a Vercel-like model. So we've got this open source compiler, but then we've got this cloud that does a lot of our orchestration for you. So you don't need to actually set that all up yourself with our compiler. We can do it for you, and we can even simultaneously compile to a lot of different hardware styles, and then do some static profiling to figure out, okay, like which, based off of everyone using the cloud, where are some pretty common pathways that have efficient runtimes, depending if I've seen, you could do some memoization to be like, okay, I've seen this kernel before. I don't even need to run it. I can just swap in the actual runtime that I've seen before. Obviously, there's a lot of buzz in this space. It's a very hot space right now. Modular, I chatted with a couple of engineers there last week, and it's interesting, but I think fundamentally they have, they're creating work for themselves by creating this language on top of the compiler. So not only do they have a compiler problem, they now have, I'm kind of just actually giving them the language creation problem because, their founder is obviously so talented. I'm like, okay, they're going to do that. Fine, even though that's very hard. But then you have to get people to actually migrate and use your language, which is non-trivial, especially when it looks so similar to Python. Tiny, obviously, this is something that inspired the project, honestly, because of the fact that they use rewrite rules that are destructive. And that means you can fall into local minima pretty easily. And actually, they're kind of doing a whole overhaul right now because of this limitation they ran into. So that's their hang up. Modal, there's no compiler. They're tied to, it's not really Docker, it's their own container style, but it's basically, it's just a flavor of Docker they invented. And obviously that has problems of having to, maintain your Docker file itself and all these dependencies. With us, you just upload your model graph and your weights, and it goes on its merry way. So kilobytes of data for this compilation versus, uploading gigabytes of your Docker file. And then you've got, these companies like Together. I'm kind of clustering in like Together, Grok, Fireworks, all of these into this last one where they sell access to their bare metal. And then they're writing they're basically hand tuning each model. They've got a bunch of engineers writing this hand written code, which obviously limits the scope of the models they can support. So they've got like, I don't know, I think Grok has like 8 models. Maybe I'm wrong there. Maybe they have more now, but it's hard to generalize that, especially when their compiler doesn't really work. All right, and that brings me to what's next for us. So we're hiring right now. I had like 2 interviews this morning for 2 roles really, a compiler engineer and a GP engineer. And pretty much you can ignore all this text. The compiler engineer is to help restrict that search space and condense it and search through it smartly. The GPU engineer is to help forward deploy models. So we have about $6 million worth of LOIs of companies that really want to use our compiler. But right now, because the search space is so constrained, it's not really end-to-end automatic to run the compiler. So we need someone to help us out with kind of forward deploying these optimizations. And basically, the approach now that we take is we actually go back to the model graph and we chunk out the layers themselves and then feed them through the compiler, get those optimized kernels out, and then string them out in a dispatch list, right? And then serve that on our cloud, or in some cases, we're doing some on-prem deployments as well. But obviously, we need someone very talented at CUDA to help us do that. CUDA, because that's what everyone's using today to run their hardware. Yeah, that's Luminal. I'm sure there's always tons of questions, so I wanted to save a lot of time for that. Chris, what do we got?
Yeah, man. Awesome stuff.
Thank
This
you.
was exactly what I was hoping for. Yeah, so here we've seen a different approach to this problem, which I love to see. And there's a few companies in this space, even in your Y Combinator batch. But I really like
Yep.
this. I think and the code is open source, right?
Mhm.
What is going to be so I have a bunch of questions in here, but first question is, if you have open source, how are you going to make money off that? Is it this Vercel like cloud that
Yeah.
you plan to make money? Okay.
Yeah, that's exactly right. So a lot of this orchestration, right, like setting up the speculative decoding, doing multi-host stuff, like all this stuff, you can put our compiler through that, but it's going to take you months to set that up. So it's very similar to Vercel and Next, right? Like let us handle all of the orchestration, get you those optimizations automatically, or you can do it yourself if you have the resources and time. But if you just want to get to market quickly, we're going to be the best option to do that.
And who's a typical customer? Like, what's the initial customer profile for this?
Yeah, that's a really good question. So people that care about latency and the user experience that comes along with that. So it's going to be like text to speech model companies, video generation, image generation. This is actually how Fall, I hate that name. I always mispronounce it.
Yeah,
Fall
me too.
that's how they got, I think they went from 0 to $1 million ARR in 9 months, and then $1 million to 50 in like 6 months. So they focused on flux model companies, right? And they literally came in with engineers that they poached from NVIDIA to hand write kernels to optimize these image gen models. So that actually kind of like proves the need for this within at least that vertical. But that's the approach. And really, I think, a year ago, it's funny, you would have heard a lot of people saying like, oh, latency is not that big of a deal, and we're fine burning all this money. But as they keep burning that money, right? As this burn escalates, I think a lot more are becoming a lot more conscious of the fact that they need something like Luminal.
Yeah, for sure. For sure. Yeah, I mean, pretty much every customer that I talk to, is struggling with these GPUs. Either they can't get enough, or their spend is just going through the roof. They've got tons of models that they're trying to get out. They just don't have the capacity, don't have the money.
Well, and the
To
problem is
run these
every
things.
time new hardware drops, you have to rewrite your optimizations for that new hardware. So it's not just
Yeah.
like you hire some guy as a consultant to write these optimizations one time. When NVIDIA drops a Rubin, right, there's going to be optimizations that, it's funny enough, even like NVIDIA won't know how to write sometimes. That's
Mhm.
why you saw cuBLAS, which can do some of these more basic kernel swaps. It lagged by a couple months when Blackwell came out. So Blackwell was actually worse for a while than the Hopper series, because cuBLAS wasn't updated with with, I believe it was the fact that the tensor core size had changed and like a couple other things. But even NVIDIA themselves with their own library are behind their hardware, right?
Yeah, tensor memory. Yeah, there's always new, types of hardware that. Yeah. So that's a good point. Let me just cycle through the questions here.
Yeah, please, please.
So,
There's so many. I would love if you could just read them off.
so Luminal is not planning to be a PyTorch backend. Is that correct?
Say more about that. Like, can you?
Yeah. Well, you kind of mentioned like it's a slower process because of the search, and you're spending a lot of time. So it's not a just-in-time compiler.
Mhm,
It is an AOT compiler, but to become a backend like Triton, not the
mhm.
NVIDIA Triton, but the like
Yeah, yeah.
OpenAI Triton.
Right, right.
That's really become, and what's it called? AOT Autograd, and actually there's another Dynamo, right? The Torch Dynamo.
Yeah, yeah, yeah.
So all of that is being powered by Triton kernels for the most part, and OpenXLA, for example. So that's another Torch backend for PyTorch compile. And I always ask the modular folks like why they don't want to become a PyTorch backend, and my sense is, you know, they don't want to just be seen as a PyTorch backend. They want to be the
Mhm.
runtime environment. They want to be the inference engine. Much more. So, but will I ever say PyTorch compile backend equals Luminal and it go
Yeah,
through and mm,
yeah. I mean, I think what it boils down to is we just want to own inference, right? Like we don't really care about the training at all. And whatever framework
interesting?
you want to use for that is what we want to support. So all of our functions that we're writing right now for the Python bindings, it's going to be as easy as import Luminal as torch. So I guess the
Oh,
general
interesting.
yeah, yeah. So the general flow of how a researcher would use this is they write their model in PyTorch, right? And then all of our front end is written the exact same way, right, as PyTorch methods, so that when you're done with all your training and evals and everything looks good, you can literally just swap one line. You can do import Luminal as Torch. It'll do our compilation, and then you can deploy it with one line as well.
Interesting. And you mentioned, I think, what was it, 1,500 operators or something? What was
1200 in PyTorch graph, yeah.
in PyTorch Graph? Those. So when I was, preparing for the book and really diving deep in, there's something called prims IR, like primitive,
Mhm.
intermediate representation, which is part of like AOT undergrad and Dynamo and all that.
Yep.
And those 1,200 actually break down into only 250. So said differently, to become an official Torch compile backend, you need to at least implement about 250 primitive operations that things get lowered into, and then everything's built on that.
Yeah, and
So
that's what takes a while is you have to do this translation, right, from the torch graph to RIR. So you basically just have to take each function, figure out what primitives in our simpler IR break down
got it.
that function, and then for example, like the convolve operator, right? Like how do you structure um, the sum reduce to construct that
Yeah.
properly?
Okay. And another question that just popped into my head on this is distributed. So, and expert systems obviously are the superior choice these days. So, and there's a lot of communication, a lot of nickel, communication going on, a lot of Nixel, right?
Yep.
Yeah, the new NVIDIA protocol. So how savvy is Luminal to distributed like communication and overlapping communication with the compute kind of thing?
Uh, a little bit. Can you say a little bit more? Like, give me I usually operate best on like analogies.
Yeah, yeah. So, I mean, these like experts, for example, right?
Mm,
So it's a little bit easier to talk about on the training because, yeah, everyone knows, when the
yeah.
backprop's happening and the gradients need to be all reduced. But, there's with these expert systems, federating out to multiple experts, running
Okay.
and then the data coming back together. So specific to the
Got it.
inference.
Yeah, so mixture of experts orchestration is something we're still
Yeah.
working through. That
Got
obviously
it.
gets complicated. So we work best on dense models right now, but it's
Yep.
possible. It's going to take some time for us to figure out.
For sure. Yeah. And I mean, thanks for the honesty, because this stuff all
Yeah.
comes out at some
Well,
point. And I'm
it's
sure
open source, so it's like
it's in the roadmap,
you'd see
probably.
yourself. Yeah, you'd see yourself if
Yeah.
it works or not.
Yeah, man, this is so exciting to see this kind of stuff, coming together early on. Okay.
Let's go
Is
through
there,
here. Yeah.
yeah. Is there any more you could talk about the RL? It sounded like you folks maybe are just kind of starting on the RL path.
Yeah, we're frankly just really just starting on
Okay.
the actual searching through the space.
Yeah.
We've got someone right now that's actually trying to just in our GitHub, trying to figure out how to implement efficient RL. So the idea would be like if it's seen a portion of the graph before that you can run it through some simple RL model and it'll say, oh, okay, I know roughly where to look in the search space based on what I've seen before. So the outputs there would obviously the inputs would be the portion of a graph. The outputs would be runtimes, right? And then you could just kind of point to the location in the search space to start.
Sweet. Love it. How about integration with like profilers like Insight Systems, Insight Compute, PyTorch Profiler, HTA, things like that? I think it was on one of your slides about profiling or static profiling.
Yeah, it's something like frankly, that's something we also need to do a lot of work on. Um, we haven't really considered integrating with any of the existing ones out there, and frankly, I don't even know, how well used they are. Um, but yeah, that's just something actually I have kind of a blind spot on, to be honest. I'd love to hear from the community though what they want. And by the way, speaking of that, I should drop our Discord so you guys can actually join and suggest some of this stuff. Let's do this. There we go.
Yeah, drop it in. Sweet. Yeah, I mean, ultimately, that's
Oh, hold
one
on.
way of.
And we did to host some panelists. It looks like I can't post to everyone.
Really? Sorry.
Yeah, it's okay.
I'll post it here. And actually, I'm going to join while I'm here as well. So I think this is extremely
Let's read
valuable.
some of these. When is mixture of expert support expected? Yeah, we have a contract right now where one of the milestones, Sunjan, is mixture of expert support. So that contract is due by February, so at the latest then. But if we get it done earlier, obviously you can learn about it by joining the Discord and checking for updates there. But that actually is like one of the promised milestones of one of our contracts, so it does need to get done pretty shortly.
And by contract, do you mean you've got a contractor working on it, kind of thing?
Yeah, exactly. For a
Cool.
deployment for someone. Yeah. So they need mixture of expert support.
Sweet.
Let me read this. If we have strong PyTorch engineers who can profile our video gen inference pipeline and get everything running on GPU instead of CPU, how much value is? Yeah, the value, Sam, is going to be for you in particular, it's going to be having to recompile. That we can recompile to new hardware or alternative hardwares that may be cheaper. So we are working with some alternative hardware providers to basically. I'm sure you've heard of these like general purpose GPUs or obviously the TPU. So hardware like that, more exotic hardware, that you'll get better performance or at the very least equivalent but cheaper inference out of. So there's multiple values there. It's one that you don't need to keep having your GPU engineers rewrite these optimizations, and then two, that you can get some savings on the back end of that too. Okay. So is the Luminal open source compiler limited to only NVIDIA architecture? I think I just answered that. Is there future roadmap behind this current scope? Yeah. So today we support Metal and are continually supporting more and more CUDA. This actually started as an edge computing project, which is why we support Metal so well right now. Obviously, that's not really deployed in production too often. So we're rapidly ramping up CUDA, but that's also why we're hiring this person on the right here to help us with that. Oops. Okay, I'm still here. Okay. Where does AMD, Cerebrus, Etched, etc. fit in here? Yeah, I mean, there's a lot of people trying to break down NVIDIA's CUDA moat, and hopefully we're going to be helpful in doing that. The empirical proof there is that it's very hard, right? Like people have been working at it for, in Grok's case, 9 years now. So it's taken them, and I think the real issue is that people are approaching this hardware first, right, rather than software first. So our approach is assume nothing about the hardware, assume everything you can about the workload itself, and then cater it to the hardware, versus trying to build hardware guessing what the architecture is going to be and trying to build the software backwards. It's obviously just an approach that's not working. Etched in particular is almost like the antithesis to what we're doing, right?
Yeah,
Etched is
yeah.
like fully assuming everything about the workload, whereas we're trying to keep it pretty general and high level. And a lot of these compilers, the problem too is that they're trying, because they worked backwards like this, they need to do a lot of scheduling. So you end up with these like what is it called? Like very long instruction word compilers that are, like God compilers, like really you have to like figure out everything about the workload, which is naturally extremely difficult. So I'm pretty bearish on their ability to figure that out. But hopefully they can use Luminal, and then we can, they'll all use Luminal, and it'll be fine, and we'll make a lot of money. Okay. We already answered the stuff about RL. Repo link is in there.
Yeah,
Okay.
question about multiple GPUs. That's kind of what I was asking. Yeah, about the distributed.
Yeah, that's something that we're working on right now. So that's going to have support in the cloud for sure. It might be something we don't. There's aspects of the cloud we obviously want to keep closed source, just to be sure that it like is better, right? So we might not release that orchestration in the compiler, or we might. It's just you always play a balance with this stuff, but we'll see. Yeah. Do you target FPGA for inference as well? We will. Yeah. Not right now, but we will. Worked with GB200 with InfiniBand. OpenAI is using this hardware for yeah. We have significant reservation, but curious if other folks have seen value with alternative hardware. I don't know, Chris, have you seen people get a lot of value out of alternative hardware yet?
Specific workloads, and I'm a big NVIDIA person. I'm a longtime shareholder, and I've just followed them, and I know CUDA pretty well. And but yeah, I mean, there was just a very interesting Twitter, X thread recently where someone highlighted that PyTorch has about over 200 tests that are disabled for the AMD
Oh,
chip. Did you see this?
yeah. Oh man, that was funny.
Yeah,
If
like
you,
Dylan Patel. Yeah.
yeah, that guy's a hoot. I
Stay
did
on his
see
good
though.
side, right? Yeah, you want to stay on his good side.
I did see though, someone was telling me, this is hearsay, I didn't look myself, that a lot of the tests were redundant though. So yeah, I don't know if it's like a full 200 that were turned off.
Yeah.
But anyways,
Oh, okay. Yeah, I mean, I've definitely tried AMD's little dev cloud. It's hard to get anything working in there from my standpoint. So, hoping things get better there. I know they've got a new VP of AI, and she's really starting to make some changes. So, but if I was going to make a bet right now, I just stick with NVIDIA, pay the premium, get your shit
Mhm.
done. So
Yeah.
yeah, awesome.
By
But I don't want to
default,
keep you too much longer. Oh yeah,
I just
go
want to
ahead.
answer this last one. By default, does it make optimizations of CPU interfaces or pure GPU? Excuse me. Right now, it's pure GPU. You specify the hardware target, and it's CUDA or Metal. There's a weird architecture that we might support that needs CPU support. And if that's the case, we'll probably open source that. So yeah, that's it's a non-answer, but it's a strong maybe. But right now, only GPU support.
Cool. Hey, bud, thanks so much, man. Let's keep in touch. It sounds like you guys might have something coming out in a couple months. We can
Oh
make time
yeah.
for you. Mhm.
Also, if someone's interested in hiring, let me drop the best way to do that. You can email me here with your resume and GitHub. I
I'll
think you're
send
gonna
it
have
to
to
everyone here. Yep,
I think
yep.
you're gonna have to reshoot that. Just email me there. You can also find us on Twitter. It's at Luminal, at Luminal_AI, and you can just DM us there as well.
Luminal_AI, DM, direct message, right on.
I refuse to call it X. It's always Twitter.
I know.
It's such a
Yeah, do you
bad
still
name.
call it Facebook too? Yeah, you don't call
Yeah,
it Meta.
of course.
All right, man. Yeah, good
All
luck
right.
to
This
you.
was great, Chris.
Yeah, let's keep in touch. So thanks, bud.
See you guys.
Have a good week.